Okay, thanks, Alex. Thanks everyone for attending this session. So this session is near real-time data for air quality and health application. My name is Jingqiu Mao. I'm from University of Alaska Fairbanks. Our first speaker is supposed to be Pawan Gupta, and I think Alqamah Sayeed will step in for him, and he will talk about satellite and model data into decision-making system. It's all yours. Welcome.
Hello everyone, my name is Alqamah and I'm covering for Pawan. Unfortunately, he had COVID on Monday, so he was unable to come. So I'm just discussing what project he's currently working on. So one of the main, Lucas Tran, Singlang Zhao, Zai Dong, and Dimple are team members. And here's the list of HAQAST team and Tiger team member list. And the first thing we are doing is integration of satellite data and model outputs in air quality monitoring and forecasting system. So here we integrate satellite data with AirNow network and try to provide EPA with PM2.5 concentrations. So for this project, this is a Tiger team project from 2021 to 2022. We are integrating satellite data to derive PM2.5 into EPA's AirNow system. And this is a collaboration between NOAA, EPA, and HAQAST. HAQAST is working as intermediary between NOAA and EPA. So we have NOAA, which provides satellite data, and then EPA is the agency which is going to publish that data in AirNow system. This product will address the data gaps which EPA has. So EPA mainly right now have AirNow system which have point source data, and this system will address the data gap in those point measurement systems. The system will also alert public during severe smoke and dust events. This will also identify where we need more monitors to monitor PM2.5. And it will also identify the zones where we have non-attainment as per EPA. And it will also promote some EJ studies and health studies. So this is a brief overview of how this is going to be done. So we have two geostationary satellite goes east and goes west. This is not the figures are not time synchronized, so this is just representation. So we have AOD from goes east and goes west, and we already have PM2.5 through geographical weighted average regression, which provide PM2.5, and we have a paper from Dr. Shang and Dr. Shobha. So the first task was to combine both east and west data into one combined data set. And then the next step was to evaluate that data and characterize errors. Barron here is going to present next following me, and he will discuss more about that thing. And then the further step was to develop an algorithm which uses a machine learning approach to bias correct and implement that bias corrected PM2.5 in the EPA system. So the green color means that these steps are almost complete, and the yellow one where we are still working on developing a pipeline in the AWS to process data, and then we will work with AirNow team to implement these data. And the last step will be communication through developing user guide and training, which will be done later this year. This is a slide from Jingqiu Mao groups from University of Alaska. In this project, so the issue with goes east and goes west is that it does not look in the Alaska because of the higher latitude region. So the idea was to use a polar orbiting satellite like MODIS or WHEELS to integrate it with a model to produce PM2.5. I don't know if Mao is going to present it later or not. So this here model AOD is derived from GeoScam and from Modis and Weaves, and we developed they developed a relationship between AOD and PM 2.5, which was evaluated through purple layer and regulatory monitors. And the left right-hand bottom plot shows the comparison of Modis AOD and AirNet AOD. Then this is another project we are working on with US embassies. This is in collaboration with US Department of State. Mary here is going to have something in this presentation. This project is also worked in a big team from Marshall and Goddard. We have a partnership from DOS, HAQAST, USRA, and University of Huntsville, University of Alabama at Huntsville. So, so there are three specific tasks in this project, where the first is capacity building on satellite observations. The second task is providing PM 2.5 forecast and historical data record for the US embassies, which are around 270 plus embassies. Right now we are working with, we have done for 70 plus embassies. So the flow chart represent a basic methodology how this will be done. So we will have a surface measurement, satellite measurement, and model simulation, and all these three will be used in an advanced machine learning algorithm to produce PM 2.5 forecast and also produce historical data record of PM 2.5 for 21 plus years. And this is one of the application where cloud-based system will be developed. So GeosFP will provide aerosol and metrology. Then we will have a machine learning algorithm that will train Geos with ground data. And then we will produce bias corrected PM 2.5 once per day and 3-hour forecast for next 72 hours. A Python package is already developed and deployed on AWS to download, process, and run MLA. So this whole package is currently running on AWS, and the middle figure you see is that the actual real-time result which is being produced on AWS. It's not open to public right now, I think, but it will be soon delivered in the end of summer. So this product is a real-time product, and it will be in real time. It can also be evaluated. So the system is currently running, and we will be able to deliver it by the end of summer. There is another example where we did forecasting validation. So the top panel is Geo's FP estimated PM 2.5 with observed PM 2.5 for Emory, and the right one panel is for Delhi. In the top panel, there is scatter plot for the observed versus predicted. And you can see that there is a huge improvement in R, and bias was reduced significantly with the use of deep neural network. So this methodology is already implemented for 70 plus embassies on AWS, and we have validated 15 plus embassies, and we are targeting to deliver it in summer and do the validation for remaining embassies. We will also extend this forecasting system to next 270 plus DOS locations, and we will also provide a user guide and training during fall 2022. So the green means we are already completed that, and next are the plans which we will be doing in the future. Sorry. This is another example of how well the model is working. This is a 21-year time series record. The panel shows hourly PM 2.5. The x-axis is observed, and the y is estimated PM 2.5 for the Bangladesh embassy location at Dhaka. You can see that the R value is 0.97, a very small bias for overall data, and we have this record for continuous 21 years, so there is no data gap in the time series. So this was the main product we were trying to develop. This product is already available in hourly, daily, and monthly and annual mean file in CSV format. This data set is also being distributed to embassy staff, air quality fellows, and their partner to be used for analysis, air quality assessment, and health impact analysis. This data is also archived at NASA Justice. I think Kevin Krabbert Tiger team has done a lot of work on that, providing these data sets. So this is continuation of the previous slide. We will develop a data user guide and do a publication in this historical data record and get it peer reviewed. Training on data set is also planned for the DOS staff and embassy staff. Analysis of ambient fine particles. So few air quality fellow are already working on analysis of PM 2.5 and fine particle in different parts of the world. So Salva is working in Jakarta, and William Danforth is working in Jeddah, and then Jose Hernandez is working with Sheikh. So these all are the projects currently Pawan's team is working on. So that's it from me.
We'll save a question for end of this talks. So our next speaker will be Barron Henderson from US EPA. Here is all yours.
All right. First, I want to thank you all for having me. I was excited to get the opportunity to come and represent this project, this HAQAST Tiger Team project. Before I get into it, one of the things I want to start with is thanking the leadership. So,
Sorry, my Zoom is not picking it up. Just give me 1 second.
absolutely.
Okay, we are rolling. Sorry about that.
All right, thank you, Alex.
Yeah.
All right, I should have started over. I'm Barron Henderson. I work with the US EPA. I'm in the photochemical modeling group within the Office of Air Quality Planning and Standards. Thank you for having me. And take two, I'd like to start by thanking the leadership of HAQAST. So John Haynes has done a great job working with Tracy to really set up a collaborative environment where both federal, state, local, all sorts of different stakeholders can come together and make things happen, right? It's sort of a safe space to collaborate and come up with innovative solutions to longstanding problems. The project I'm going to be talking about is being led by Pawan Gupta, and this is really, we affectionately refer to it as the AirNow Tiger Team. So this is the one that Alqamah was talking about earlier. So one of the great things about this is it's bringing together several federal partners that want to be working together and are trying to work together, and the expertise associated with HAQAST is helping bring us together faster than we could otherwise do. For those that aren't familiar with AirNow, AirNow is a national platform that both acquires data and distributes data. So it acquires air quality observations from states, locals, tribes, et cetera, collates that information in a way that makes it comparable and distributes it to the public. So people can go and they can look to see what is the air quality in my particular location. Now, in addition to the observational data, there are also forecast data. And again, there are many, many partners that make this possible, and EPA is just acting as a central repository. So one of the things, though, that has been interesting with AirNow is over time, as fires have increased and air qualities associated with fires have increased, the page views in AirNow have followed suit. So what you can see here is page views, and as you hit the fire season, they go way up. We can get as many as 1 million a day. And those 1 million a day are very much associated with wildfires causing air quality problems and people wanting to know what's happening. So we have this simple way of thinking about things. You look at your dial, how am I doing? Good, bad, whatever. That's great. You can delve deeper. What are the monitors around me saying? That's fine. When we get to fires, we end up in some interesting situations where we can have very strong gradients in between monitors. So you have people, for example, that we're going to pretend live right here. There's not a monitor right by them. Is the smoke blowing towards me? Is it blowing away from me? Is it affecting me? Is it not? If I just interpolate the observations, that's not really a credible way to answer that question. And that's what's happening right now. So the AirNow Tiger team is looking to bring satellite data to fill those data gaps associated with the observations. So when Alqamah was talking about Hai and Shoba's paper, it looks a little something like this. It starts with the satellite data and observations distributed by AirNow. It goes into a geographic weighted regression. Conceptually speaking, we have an individual point we're trying to predict. We're weighting the observations around it, fitting an equation, and coming up with an estimate of P of 2.5 at the surface, right? So we start with aerosol optical depth, which isn't a surface measurement. We get to a surface concept. So again, this project is building on decades of research that started really in HAQAST, which was 2 versions ago of this same general project, where they were working with polar orbiters. The big deal here is we're using the advanced baseline imager that is more like a lot of you are familiar with tempo, right? It's a geostationary, it's staring, and it's getting rapid 5-minute data over the continental US, 10-minute data over the full disk. So this lets us leverage all the skills that were built with the polar satellites and then bring them into a more rapid data set that's more conceptually consistent with trying to give people real-time air quality data, which is what AirNow is doing. So we have a broad group of people, everybody working on different things, trying to better understand the product, its strengths, its weaknesses, et cetera. I want to do a little bit of a flow chart on how this is going to work. Again, states, locals, and tribes are collecting the data. They're giving that to AirNow. AirNow is both displaying it and providing it to others through an application programming interface, an API. At the same time, NOAA is collecting the satellite data, processing it to aerosol optical depth. They then go on to produce a bias-corrected product and couple it with the air quality observations. When they do that, they bring that together into that geographic weighted regression we were talking about earlier, which theoretically could produce the product directly for AirNow, but instead, we're going to introduce a bias-corrected term even after that process. In addition to doing the bias-corrected web service, which will then be redistributed through AirNow, we're going to need to do periodic evaluations to make sure that the relationships we're seeing in the product hold. So if it does well in one place, it continues to do well in that place. This is important conceptually because the observational network is currently in a massive transition from samples that are an integral over a day to real-time samples in the measurements. So Haisley, Haizhang, and Shoba and I are working on a paper where we're characterizing the performance of this. This is a tenfold cross-validation of the geographic weighted regression. And on the left-hand side, we're looking at the hourly performance. And on the right-hand side, we're looking at the daily performance. A couple of things should pop out to you. There are areas in the hourly performance. Here we're looking at the R squared. Below we're looking at the root mean square error. There are places where it does really well right out of the gate. Not a big deal. There are other places where the root mean square error can be quite high. Those are the same places that wildfires lead to really large concentrations. So it may be a large root mean square error, but it may not actually be a large relative error. So there's things to look into. There are also places where the correlation starts off not so great, right? And as soon as we introduce temporal averaging, we go to a daily value, we start to see better performance across the board, which is sort of what you would expect. I started earlier by saying AirNow puts out a nowcast, which is equivalent to a 3-hour average. So the question is, if we went back and evaluated this product on the 3-hour average, how would it do? It would get rid of some of the noise from the satellite data, where we just have a little bit of noise associated with clouds, et cetera. But it wouldn't probably be as good as the daily value. So that's something we have in progress. The other question we have then is, how do the performance we're seeing here relate to monitor density, land use type, and fire prevalence? One thing I'll point out is in the AirNow system, there are only 3 real-time monitors in West Virginia, and yet the performance is relatively good there. So there's some correlation to monitor density, but less than we initially expected. So if we move on and we look at the validation with respect to other parameters, here we're looking at it either as a function of AQI, which is the air quality index. Here I'm showing moderate, unhealthy, and hazardous categories of data. And here I'm looking at the performance as a function of land use type. I'll start over here. Initially, I expected there to be a strong relationship between land use type and the performance of the model. We really don't see that. It's generally the same with the outlier of barren land. Barren? But it turns out that that's really just a coincidence. There's one observation in barren land. So we're not going to focus too much on that. But if we look at the performance within moderate air quality, what we see is we're evaluating the performance as a function of distance from an available observation. So we're holding an observation, we're saying how far is the closest one that is helping to drive this relationship. We don't see a systematic divergence as we move further and further away, which is a really good sign. We also don't really see a consistent signal in the unhealthy, but by the time we get to the hazardous, these are the really large concentrations typically associated with fires. We start to see a relationship. As you move further away, the performance gets worse. That's probably related to a handful of things. One being that when we have a fire, we'll often saturate the AOD. The AOD signal might be identified as a cloud and therefore withheld. If you withhold all the high values from the AOD and then you try to predict the high values on the surface, that's a problem. So that's something that Shoba and Hai are looking into to see if they can change the filter. The other thing that you end up with is you end up with only relatively far points being brought into the regression. And we know that the fire concentrations have high spatial gradients. So we would expect a relationship built from further away to do poorly under those circumstances. So that's something to work on, and we'll continue working on it. So far I've only talked about the geographic weighted regression, the spatial relationships, the relationship to land, the relationship to concentration. I want to highlight the work that Alqamah Sayeed is doing. He didn't talk about it as in depth in his last presentation, but he has a flash talk later. I encourage you all to be there. What he's doing with that work is he's starting with the product that I've been talking about so far. He's coupling it with some of the raw satellite data and bringing in the NOAA high resolution rapid refresh meteorological forecast. He's going to pair all that data and put it into a deep neural network. My glossy understanding of deep neural networks is what it means is it has multiple intermediate layers. So you're going to start with an input layer with multiple features. You're going to couple that to intermediate layers that have sort of a multiplicative property. You're going to translate that data all the way through to come up with an output, in this case, the corrected surface. What Alqamah has been able to do is show that when we took the dose PM and we looked at the performance as the concentration went up, the performance really tended to diverge from what we would want. When he applies the correction to the data, it has a clear correction at the high end. What's harder to show in this plot, and I'm sure I could have brought in a bunch of other plots, but it's also correcting some of the data at the very low end. So what's neat is his correction algorithm is not just correcting one end at the expense of the other, but is really improving things across the board, which is pretty fun. And I'm sure there's a lot of progress to be made, and he'll talk to you more about that later. But one of the things that I wanted to highlight is earlier when we were looking at the maps, I pointed at the Arizona, New Mexico, Texas area as areas where the correlation wasn't very good to begin with. And the root mean squares were not very good either. His bias correction tends to make really nice improvements. Someone highlighted to me, these are, in terms of absolute magnitude of our square, it's not very big, but in relative improvement, that's fantastic because we were doing pretty poorly there to start with. So that's a big relative improvement in the R squared. And the RMSE is also really dramatically improving in those areas. So that's a big improvement in the places that we really needed it. So, you know, hats off, Alqamah. So once we have this data, what we need to do is find a way to bring it into AirNow. We can't disrupt everything by just throwing out one thing and bringing in another. So we have sort of a staged implementation plan. We start with the fire and smoke map, which tends to be more on the cutting edge. It brings in more data sets than people might be used to when they go to their typical dial, right? In that case, we can do a pre-release for our very close partners that are providing us data and providing us forecast data, because we really don't want to surprise them with something that's not performing well in their area and causes problems. After we do a pre-release of that data for our partner review, we could then move that to public, which is still not in the primary flagship reporting part. At some point, we would then bring that into a data fusion. So where you have an observation, the observation will always be better than the model, and we'll want to do some sort of fusion to bring these two products together, which would create a single product that could be distributed through the flagship Air Quality Now communication. And ideally, what that would allow us to do is stop reporting at large areas and start reporting with relatively fine gradients. So right now, there are what we call reporting areas. And so we do create a textured map, but then we really just report a single value for an area. And if we could instead say, ah, well, at your house here, it's this, and when you go to work, it's that, and along your path, it looks like this. That's part of the vision for a more hyper-local set of communication. I'm already over time, so I look forward to the discussion, and I'll close it there.
Thanks, Barron, for that talk. Our next speaker is Yang Liu from Emory University.
So thanks, everyone. I'm going to follow the same line of discussion here with high frequency PM exposure modeling, a switch gear a little bit from operating systems to more exploratory and methodological development. Right, event slides. Okay. All right. Right. So the work was motivated by fire smoke, but it actually goes beyond that. I'm going to cover 4 sections of kind of our projects. In addition to motivation, study objective, I'll say a little bit about the data and model development. This includes 2 phases. We have a published study using a documented and developed kind of modeling framework. And then we've done some additional exploratory work, and we'll report preliminary results. Okay, so we've seen plenty of media coverage related to, devastating wildfires in the recent years, especially in the Western US. Wildfires can directly threaten, the ecosystem, human lives, destroy properties, forests. Indirectly, wildfires produces massive amount of fire smoke that can go downstream, further, hundreds of miles away from the source of the fire. And it's becoming a dominant source of PM 2.5 emissions, especially in the Western US. Now, we don't have a very good system to quantify fire smoke exposure at this point, because very often fires originate from far away from monitoring networks, and then it develops very rapidly, and then there's massive and very rapidly changing pollution concentration gradients, right? In addition to fire smoke and air quality per se, we have seen more and more epidemiological evidence that hourly level pollution exposure can cause us some real damage. This is just a kind of snapshot of what is being reported. This is just a subset of the health endpoints that have been linked to hourly level air pollution exposure. For example, acute coronary syndrome, blood pressure changes, asthma exacerbation, and more traditionally, people have linked that to ambulance dispatches. So in essence, you have to have health data with sub-hourly timestamps in order to use hourly exposure estimates. So there's interest in both air quality and health effect research in terms of better characterizing hourly level PM. Our current methods in quantifying pollution, we started from ground-based monitoring networks. The good thing about ground monitors are high accuracy, highly reproducible. but the limitation is spatial coverage. These are point estimates, right? From the satellite perspective, we have been using a lot of polar orbiters. They have global coverage, but very limited sampling frequency, normally 1 to 2 times a day. Now, then we had this opportunity to explore geosynchronous satellite instruments, such as GOES 16, GOES 17, or also known as GOES East and GOES West. So GOES 16, which is the GOES East, retrieves AOD and smoke masks at about 3 kilometer resolution multiple times during daytime. And our study, the initial objective is to explore the possibility of using GOES 16 AOD data to estimate hourly PM levels in California during the campfire period. This is a exploratory project, so it's not meant to cover the widest possible area and the longest possible time period. This is just kind of a case study to prove our concept. Okay. So 2 months study period covering the campfire with a little bit of a lead off and then a little bit of a aftermath. In this period of time for the state of California, we have a bunch of measurements, actually, altogether nearly 1,000 ground monitors, about 20% from HAQAST, the official network, and then 80% is actually from Purple Air. We gridded everything to 1 kilometer resolution. We calibrated Purple Air with localized GWR models before we merged them to the official data record. Altogether, for this 2 month period, we have almost 250,000 hourly measurements at 1 kilometer resolution. Okay. Just to show a little bit of the raw data, and so you can tell, because GOES 16 has multiple measurements during the day, you can kind of pick the onset of the primary plume. We were a little bit late because the fire started at around 6 a.m., but the GOES 16 picked up the plume at around 8 a.m., a little bit later when the plume is more visible. And this is the initial model input stats. We have satellite data, we have high resolution meteorology from the HAQAST, a bunch of input parameters. We have static data from land use, we have road networks to provide stronger spatial contrasts. Okay, 3 model configurations. This is the standard for the classical model with EPA input only. Sample size is much smaller, 40,000 incidences. If we combine HAQAST and Purple Air, the sample size goes to 246,000. And then we did a little bit of a twist near the end with a oversampling technique called SMOTE. This one artificially enhanced and resampled the very high end of the pollution spectrum. So only when the PM level is above 100 micrograms per cubic meter, the data was artificially enhanced by this technique. It affects less than 6% of the overall training data set. Okay, and model cross-validation results, HAQAST only, our square values are high, and I'll say why they're high. But you see the slope is off for HAQAST. So the model is underperforming when the PM levels are very high. With SMOTE model, the random forest model is better trained. The high-end noise is knocked down a little bit. So you can see the regression slope is closer to unity now. And in terms of spatial performance, the smoke features are enhanced by the enhanced model. In the interest of time, I'm not going to spend a lot of time on that. And this is just some prediction maps by the hour. Still, even with satellites, we have a lot of missing because of cloud cover. That's a kind of unresolved issue when we deal with high frequency satellite data. We still don't know how to fill the gaps. So quick summary, we think, first of all, low cost sensors are very useful because they're sometimes they're closer to the origin of the fire, but you have to put proper weighting even after calibration, right? Because the sensor network is grown more organically. There's no systematic thinking and planning of a sighting strategy, so to speak. And then we think oversampling techniques such as mode or some other similar technology can further reduce model low bias at high values. But the limitation is also here. The high R squared is a little bit artificial because the model uses interpolated ground observation layer as input. And this is commonly known in the literature called convolutional layer. It's not a true convolutional layer in the sense of convolutional neural network. This is basically interpolated ground observations. The problem with this in the fire smoke setting is the fundamental assumption is wrong because the convolution layer assumes smooth transition between monitors. To deal with that, we try something new. We introduce some multi-resolution signal processing techniques. For example, a wavelength transform. This is to say, I'm going to break down temperature, I'm going to break down wind, I'm going to break down AOD into multiple segments at different temporal and spatial frequencies. Think of it as a fancier principal component analysis. Like we break down one predictor into multiple orthogonal predictors. And then we have to do a feature selection because this generates maybe 10 times more predictors. And then we don't have that many incidents to train, but there's a feature reduction process near the end. Now we have a more granular model, a granular set of predictors that feed into the standard random forest model. And from that point, we can go on to the techniques that we know how to tune the model. Very preliminary results. We took out the convolutional layer, right? Without that, the random forest performance dropped quite a bit from 0.83 to 0.67. So the layer is very important, but that R squared improvement is artificial. Sorry about the typo, that should be a super squared. But even without the convolutional layer, once you decompose the input parameters into a transformed wavelengths, R squared goes right up. Right? So there's definitely something in the model that to pick up the high frequency changes in concentration fields. I'm not saying this is the final ultimate form of transform, but I think we're kind of on the right track. And the reason for that is wavelets are designed to capture both low frequency and high frequency non-static features in this space. And environmental parameters, by definition, are not static, right? They don't, the signal or the information doesn't have to repeat itself, especially in a finite modeling domain. So in that case, wavelets would, in theory, enhance model performance. And that's why we think this wavelet transform and its internal scaling mechanism would be a better tool to deal with non-stationary series, such as meteorology and air pollution. I think I'm over time. I'm done. Thank you very much.
Thank you. Our next speaker is Mary Tran from Department of State.
Thank you. On the count of three, I want everybody to cheer as loudly. Please don't actually. Woo! Oh my gosh, Barron! Thank you. Oh my God. I appreciate it.
I've been waiting all day.
Oh, thank you. Did you happen to smuggle some cake from the other room? Did you guys see all that cake being pushed over there? Alex said he was going to get us some cake.
Yes, yes.
Okay. Thank you so much, everybody. My name is Mary Tran, and I am with the Department of State. I just want to thank Pawan for inviting me here today. I'm sorry that I couldn't meet him in person. I've only ever seen him as a floating head. So I'm very happy to be here to represent the Department of State and the Greening Diplomacy Initiative, as well as my colleagues, Stephanie Crystal and Caroline D'Angelo, who are virtually attending. My former colleague, Dr. John Carrigas, once told me that all air quality roads lead back to Pawan. And so I feel like that's true based on my attendance today. And so I want to tell you a little bit about the Green Diplomacy Initiative. It is housed under the Bureau of Management, and we are essentially a sustainability hub for the Department of State. So we pilot sustainability programs and are an incubator for technical innovations. So a part of our mission is to advance US diplomatic leadership across the world by catalyzing projects and bolstering our partnerships in order to increase our resilience and sustainability. We have quite a large footprint. As Barron and Alqamah mentioned, we have 290 sites, and it's a lot. And we have 3 primary goals in order to meet that mission, which is to advance the leadership in sustainability and resiliency through global outreach and leveraging our large global footprint and our operations as a model, to address the risk of climate change and resource waste to global operations through innovation, like I mentioned, with our incubation of new technologies, efficiency, and our partnerships. I'm very glad that I'm the last to go because all of the work that I was going to discuss has been discussed technically already, so I can just stand here. And then the final goal is to ensure forward-leaning compliance with relevant statutes and executive orders. So the current administration has released 2 executive orders regarding climate change and sustainability, which I'll be talking a little bit about later. And so a big part of attaining these 3 goals is the department's first Internet of Things network, which includes our 3 primary programs, DOS Air, which will be the focus of today's presentation, which collects and publishes real-time air quality data at over 60, almost 70 sites, embassies and consulates that we have across the world. The second is MeterNet, which collects real-time energy data, water and gas consumption, which our Bureau of OBO uses in order to track energy usage in order to figure out ways to mitigate and reduce our carbon footprint. And then V-Telematics, which is currently in a pilot phase, and that collects data automatically from vehicles in order to figure out when vehicles in our fleet need to be replaced and how often we're using them. So it's really important to the Green Diplomacy Initiative to be able to demonstrate smart cities and smart technologies at our embassies and consulates. So for example, Embassy Baku in Azerbaijan, they were the first site in Azerbaijan to deploy an electric vehicle. And that has set the precedence for other foreign presence in the country to change their vehicle fleets to electric. And they actually did a fun carpool karaoke-esque video online that you can see, arguably better than James Corden's. So I would recommend that you Google that later and take a look. It has our personnel in the new electric vehicle that will then be replacing our overall fleet in the future. And so let's go into DOS Air a little bit. Barron took the heavy brunt of explaining what AirNow was. And so we do have a great partnership with the EPA to get our air quality monitor data up onto AirNow. And there's a separate page for all of the data at our embassies and consulates. And so the DOS Air program started, the catalyst was in 2008 during the Beijing Olympics, when we were trying to figure out a way to get air quality data about the air pollution in Beijing to protect our US athletes. And so the first monitor that we ever installed was in Beijing. And over the last few years, that has expanded greatly. By the end of this calendar year, we'll have almost 80 monitors installed, primarily PM 2.5, mostly BAM 1020, some T640s, about a dozen ozone, and then 1 black carbon monitor in Pristina. And so with the central contract that we have that started around 5-6 years ago, after that first initial installation in Beijing, we've been able to install monitors all over the world. And we had our largest order of 15 plus monitors back in 2020. The installation of those monitors obviously has been delayed, but we've been getting through them slowly. And that includes our first fully remote installations in Lagos, Abuja, and Nairobi. And like I mentioned earlier about being an incubator for new technology, at some of those posts, we were able to use Microsoft HoloLens to assist with the installation. And I mentioned that our program has a number of sites that have still yet to be installed, and we're always looking to install more at our 290 embassies and consulates. But our program focuses on sites that don't have readily accessible or reliable data. There was a question earlier in the opening session about intention and strategy, and that is our intention, is sites that don't have readily accessible or reliable data. We want to make sure that we install monitors in collaboration with these posts to protect our personnel and their families and help them make data-informed health decisions to protect themselves from potentially harmful air pollution. So our data has proved extraordinarily helpful in analyzing the impact of COVID shutdowns worldwide on air pollution. So that potentially paves the way to engage in further advancing greater pollution reducing policies and technologies in many of the world's most polluted cities. And we also have a partnership with Air Quality Fellows, which is a program that we created that the EPA helps us with to support posts and provide virtual support, which is in high demand after COVID. And so out of this program came a product called Zeph Air. And as I talk about it, feel free to grab your phones and download it and give it 5 stars blindly without using it. That would be highly appreciated. So the Green Diplomacy Initiative, with support from the EPA and the Bureau of South and Central Asia, got a request from the field that while AirNow is a great product, they wanted an easier way to get immediate notifications if the air quality changed. And so using the AirNow API and our engineering and development team, we created Zeph Air, the US State Department's first air quality mobile application, which you can download either on iOS or Android. And this is a way for you to easily access clear and concise, reliable air quality data from our reference grade monitors that are currently installed. And so with this, you can receive push notifications if you log in, create an account, subscribe to a primary location, and then you can subscribe to secondary locations afterwards to receive push notifications when the AQI level changes at selected locations. You can also use this without signing in for an account. You just won't be able to register for push notifications. But with that, you can also set user preferences for different health messaging. So if you want to denote yourself as a sensitive user versus a non-sensitive user, you can do that, and you'll get tailored health push notifications based on that selection. And so through the app, you can view hourly, 24-hour data, and weekly data as well. We also partner with other government monitors. So we also use the OpenAQ API to pull in low-cost sensor data and some partner data from Singapore, Thailand, Canada, and some countries throughout Europe. And so one of our biggest collaborators is NASA, which is why I'm here today. We collaborate with NASA on the Maya project, which Yang has talked a lot about and you guys heard about in the opening session, so I won't belabor any of the technical capacity of it. But through our collaboration, we've been able to deploy surface monitors around the world, including AMODs and ethylometers. And to date, we have helped NASA install and deploy AMODs and ethylometers in Beijing, Addis Ababa, New Delhi, Johannesburg, Tel Aviv, and Taipei, with more to come as soon as our agreement is finalized. And like I mentioned, we also work closely with Barron on the City Air Quality Forecasting and Analysis System, so CARES, which we want to integrate that research and data into all of our products because we don't currently have forecasting data. It's very important for us to implement that technical capacity to enable the integration of Earth observations into our existing decision support tools like Zeph Air Mobile, Zeph Air Web, which is our advanced analytics dashboard that we'll be deploying soon, and the current bidding tool that enables our personnel to make more informed decisions about environmental air quality when they're looking to bid for places for their next assignment. So additionally, this data will be useful in ongoing department health studies, developing policies, and investing in exposure for US personnel and their families, and increase engagement with host governments and other air quality partners. So we're very grateful for all of the work and collaboration that we've had with both Maya and the CARES program. And like I mentioned, we are constantly looking to partner to increase our technical capability. Like I mentioned with Barron, and we work closely with Phil Dickerson with the EPA to deploy low-cost sensors and integrate that data into our products. We also co-locate with our current reference grade monitors in the DOS Air network, and we also collaborate to identify air quality fellows. So the Air Quality Fellows program, we work with US-based air quality experts across multiple industries, such as universities, academia, private sector, et cetera, to provide additional support to Post in our DOS Air program. And if you all are welcome to apply to it, if you are interested, the applications will open at the end of the summer, beginning of the fall, if you want to support one or more of our posts abroad. And some of those projects have included indoor air quality analysis, built-in capacity for air quality monitoring, and much more. And that's something that you can discuss separately with the post that you're supporting if you choose to do this. We also separately worked with the Earth Day Network and Wilson Center to create another mobile application called Earth Challenge, which advocates for citizen science data and collects citizen science data. So you can also download that if you would like. But we're also always open to partnerships and new initiatives because moving forward, we hope to integrate new programs into the IoT network, including solar and water meters. We want to continue our research to integrate forecasting and low-cost sensor data. And additionally, our climate and sustainability working group that came out of the recent executive orders is working on department-wide policies. And you can check out the Department of State Sustainability Plan online. Just do a quick Google search and you'll find it. It'll be the first one that pops up. But I appreciate all of your time, and I know we're going to jump into questions for the whole panel. So thank you so much.
Very nice talk. I think now is the phase for panel discussion.
Sure, so yeah.
Let's have all the panelists come friends and they can answer all the questions. So Alex, maybe we should start with the question from audience first. Yes, please.
You have a question for Mr. Henderson. I'm David Fadgett, I'm the Director of Geographic Information Sciences Lab at Tennessee State University. You mentioned that you had 150 organizations that are obtaining real-time PM 2.5 information. Who are those? Were they grassroots organizations, college, university?
Yeah, they,
So
Phil, oh, that's right, I should
maybe
repeat.
repeat the question. Maybe you might do that there.
Sure, absolutely. I'm going to summarize the question as who are the 150 plus partners that AirNow works with? Yeah, and you started it really well by saying it is grassroots, are they whatever. The first, Phil Dickerson would be the best person to speak specifically to this, but it's a broad range of groups. We have federal partners all the way down to very localized agencies. And on airnow.gov, there's a partners drop down. And under that, they've got partners classified. So if you just click on partners, it'll take you to sort of a general overview, but then there's a tab for local partners, state partners, federal partners. So it's a very exhaustive list. Even so, there are partners that should be out there that aren't. I think Shova's group in particular is being put up there or has just been put up there. Other NOAA branches were already there. And that was just an oversight that had happened on NOAA. So if you see someone there that you're interested in or don't see someone that you're interested in, let us know.
Thanks, Barron. Do you have another question for audience? Yes, please.
Thank you. I have a general question for you, and that is, Alberto Ayala, I run the Sacramento Metro AQMD in Sacramento, California. So thank you for the presentation on the campfire. We actually lived through it and survived. We're running into an issue now, and that is when we talk about real time, we all mean, I think, slightly different things. And one of the things that we need to be very mindful of is the public that we're trying to serve when we provide this information. So kudos to EPA and the U.S. Forest Service actually for the fire and smoke map. But one thing that we're running into is if we look at the AirNow side, and then we go and look at the purple air side, there can be differences because the gradients in terms of space and time are very sharp. And even sub-hourly data is what the public is demanding. So my question to you all, as you're integrating these tools, what is the upper limit in terms of when we say real-time data, what can we actually do and deliver to the public?
Yeah. So on
we
the,
should repeat the question, maybe?
Yep. So, and I'll summarize and look for a nod that I've gotten it right. So real time can mean many things to many people, and real time means different things when you have very sharp gradients than it does when you don't. So what does real time mean in the context of the project we're talking about here? So from an AirNow perspective, there was an analysis done that I would love to see the primary analysis. I'm not as familiar with it, but I've got the output from that analysis, which is that a 2-hour lag is something that is largely acceptable in the context of an AirNow delivery. So, obviously you want to know what's coming next, but a lot of times by the time you're looking for the data, you're understanding what we're exposed to and are being exposed to. So about a 2-hour latency is something that would be deemed acceptable in that context. And one of the things that we did when we looked at this particular project and have been working with Shobha's team on is making sure we can meet that 2-hour latency. My understanding is that if you want to make sure you have full AirNow data from the AirNow API, you need about a 20 to 25 minute lag. Then there's some amount of time spent doing the fitting. There's some amount of time spent doing the correction. And my understanding is right now we're kind of at the hour 30, hour 45 for the whole cycle. So bringing it down from the satellite, fusing it and getting it out.
Yes, I guess, okay, let's finish the question. I said another part of the question is that how to reconcile the difference between purple air and the AirNow site. I guess that, right, that's another part of the question, that what can we do? I'm not sure if panelists have any thoughts about that, because purple air definitely give you different numbers than AirNow. How would you reconcile that? Any panelists would like to speak up for that?
I would say that with the low-cost sensor deployment that we're doing with the State Department, a lot of our personnel and the locally employed staff are currently deploying their own low-cost sensors like purple airs, IQ airs, clarities, and through a survey and just field testing, we realized that there were a number of low-cost sensors being deployed in their homes and outdoor sensors, and we want to make sure that they understand that we have the reference grade monitors at some of these sites. And so what we've done is we started a pilot to co-locate these low-cost sensors with our reference grade monitors in order to analyze the data and compare it against our reference grade data. And so that's a step forward in how we're trying to figure out a way to get our personnel the most real-time data as possible without them worrying. And I was talking to Steve about this earlier from Reason Meter about how sometimes we have our personnel put their purple airs right next to their stoves and they're cooking bacon. And they're like, oh my gosh, the AQI is 450. And so we just want to make sure that that type of concern is mitigated through our co-location and our data analysis, as well as an understanding of how short-term exposure versus long-term exposure is going to affect their health. That was a great question.
And to add a little bit to that, like Mary said, the low-cost sensor networks have grown more organically. So there has to be some sort of education going in. I think EPA is starting to do this. EPA even published a calibration equation. But when I guess when purple air is injected into AirNow, there has to be a filter. There has to be a calibration before it can be kind of pushed to the public.
Yes.
Before we move on, but it is certainly true that even if it was calibrated, even if it was perfect, which it's not, and there's a lot to be done. But even if it was, just the spatial locations are going to be very different. And one thing we know about AirNow right now is when it fills in between the monitors, there's an inverse distance weighting squared to the 5th power thing, right? And we know that doesn't account for any of the known transport distance and directions and whatever. So we know that there will be times where they disagree if you're comparing the interpolated value to the AirNow. Or there's great examples where a monitor went down because it was taken off because of the risk for fire, that sort of thing. And when those monitors are gone, it's going to tell a different thing in that location if it's interpolated from far away. So there are some things that need to be addressed by calibration and education. There are some things that need to be addressed by finer data, with more realistic gradients, and there's some limit on the improvement we can make.
Thanks. Sorry, Jeff.
Yeah, no, that's all good. It's important. So Yang brought up an important point that had me thinking about all the talks. So the issue of when you're doing real-time satellite informed air quality, you're missing data a lot. Either it's nighttime or there's clouds, or the smoke is so thick that GOES says it's cloud. So this creates some dissonance when you start putting in an AirNow. So I don't think you addressed that point. So do you just sort of flip to the old school formula when there's not a satellite retrieval and that sort of thing? And then as it moves towards regulatory, what sort of dissonance does this create? Or we're not even close to becoming true regulatory with the satellite informed. Yeah, I guess I was thinking about Barron's most, but it could be for everyone.
Maybe let's read your question first.
Sure. No question.
You can't kind of do the way I did about it. I said, we don't know what to do about it. Like,
I just got thrown under the bus, to be clear. Yeah, so the question was, the satellite data has observational gaps, typically due to clouds, sometimes due to deep smoke. When you're trying to provide real-time data, you create a problem there, right? So when we have the surface monitors are providing continuous data, there's no problem there. It is true that occasionally a monitor goes down and gets pulled out, but generally speaking, we have a bigger problem. So yeah, 2 or 3 things to say about that. One, in the original HAQAST project that tried to do this based on MODIS, right? You have 1 overpass time, and the amount of spatial coverage is about half of what we get if you look at GOES in total over the day. But any given 1 hour, 2 hour, 3 hour segment is going to be missing data. So when I talked about the 3 hour average, trying to approximate the AirNow, what we're really doing in practice right now in terms of our testing is if there's missing data for 1 or even 2 of those 3 hours, you're still reporting the average, which turns out just to be the 1 hour. So you're getting better spatial coverage than we're used to with the previous type project, but it'll never be perfect. And the question is, what do you do when you have a gap? And there are 2 or 3 projects going on at the EPA right now with respect to AirNow. So one, we're creating this fused product that will have better spatial coverage, but it will always be incomplete. The quick thing you could do is then say, okay, well, depending on how far you are from an observation, you're just going to fuse into that inverse distance weighting. But the goal is to go beyond that and take something like NOAA's operational air quality forecast. It's already out there. They already do a bias correction to that. But then we're also looking at incorporating both the AQS and the purple air in some sort of a larger machine learning bias correction to the operational forecast. And so then the idea would be to fuse those 2. But that's still an idea. It's still a work in progress.
And then at night, you'll have to lean on the model.
Also, a chat that just came in from Shoba K just said that geo-exo atmospheric composition instrument will have a day-night band that can provide nighttime fires and smoke information, but we have to wait 10 years for that mission to happen.
Very helpful. That's very helpful.
Another question, because I do want to get the online questions answered. There's one again from Shoba, and then this one's for Mary. Is MeterNet data available to the public?
That's a great question. Do you want to answer that one?
No,
I'm joking.
no.
It is not. It is not. That's currently just for internal personnel to analyze. But that's a good question.
Thanks, Lee.
Just on the missing data, Jingqiu has done some really great stuff where they do fusions between raw model and when they're able to fuse the data. And so that's why I thought you might want to speak to that in particular.
Okay. I can speak to sort of the methodological development. It's a very complex issue. We've tried several ways. One is, like Barron said, to fuse multiple sources of information. And it creates all sorts of misalignment problems that you have to deal with. Another way is to really go by brute force. We built two sets of models with and without the satellite input, and somehow homogenize the two. That way, you got complete coverage regardless. That's another set of problems that you have to deal with. My gut feeling is I don't see a mature framework going out, but the problem is solvable, right? It's just a matter of how much money EPA wants to dedicate to this, how complicated you want it to be. The trade-off between time and spatial and temporal resolution. And the issue with that is higher temporal frequency demands higher spatial resolution. So they have to go hand in hand. And that's an end to the square issue in terms of resources, right? It's a solvable problem, but it's going to be an expensive problem.
I see there's a question from audience.
Go ahead.
Sure, thanks. When your work highlights that maybe a certain hemisphere consulate is perennially challenged by bad air quality, or if it's forecasted to be bad in the coming days, are there any tangible things that embassy staff will do, or do results get translated to local languages, local ad campaigns to raise awareness on kind of that back end with the local folks?
Of course, yes. So that's a really good
That's
question.
good question.
Oh, of course. Thank you for reminding me. So correct me if I'm wrong. The question was, what are we doing to communicate the air quality data that is being collected to either our personnel or the locally employed staff or the local community? Is that correct?
Yeah, exactly.
So when we deploy air quality monitor, we work very closely with the management officers and the public affairs officers at Post in order to give them learning resources to disseminate both at the embassy or consulate and the local community. And there are translation services available for the data that's coming out. They of course can go on AirNow and download that there, but we have ready templates and communication products to communicate their quality data.
I had a question just about quantum computing and whether you're thinking that way. You know, Feynman writes that nature is not right classical, it's quantum. And I know that we're not quite there with quantum computing, but just thinking about it, it seems like all the financial people are lining up to use it, the encryption people are using it, but I see nothing about air quality people when I'm out there Googling. So I'm just wondering if you might be able to talk about that. Is anyone thinking that way? I should ask.
So I think there's
So
some.
can I read the question?
Yeah.
I guess the question, I can do the service this time.
Why aren't we doing quantum computing already? Is that fair?
Yeah. I know we aren't there quite technologically, but at least, right, a lot of people are lining up, right? A lot of money is going in, a lot of people are going, oh my.
Yeah.
When this thing becomes available, we want to be the first in line to use it.
Yeah, and I think that there's a really interesting thing, and I'm going to step back from quantum and just look at the GPU. So we know that the GPU computing would be faster for the types of things we're doing, and yet there's been a relatively slow migration of our code to that. And so I think you're in an interesting space where the type of people developing the software for this type of work are typically scientists who have computing capabilities, and it's more rare to have a completely computational person building it. And so the migration then to the faster computing usually requires, quite complex adaptation, either in the languages, certainly in the compiling, certainly in the application. And so I think that's part of why you see the lag. And I don't have a good answer for if anyone has started looking at that, but there have been, I think in the last 3 or 4 years, a couple of GPU papers where somebody did the hard work of translating some of our models to GPUs and distributing them. So that's not a great answer, but yeah, I think that's why it lags, is because I think in the financial sector you have, and I don't know, right? I'm at a very different sector, but I think you tend to see people employed to do the programming, right? It's a little bit different.
Yeah, I agree. We're in a situation where the hardware development precedes the software development. And then when you talk about quantum computing or other high-end computing, first thing they want to do is to put the money where the highest return is. You probably want to use that to predict stock market movement. That will be the top priority. And I don't know where
I'm not using
EPA
it to
stands
save
in
9
that.
million lives, right? Rather than making a billion extra dollars.
Yeah,
That's just my opinion.
Wouldn't it be nice if people accept that notion that life actually is worthwhile? And then like GPU, yes, if you look at the software development in universities, we tend to use free software. So a lot of the code packages are written in R. R is not a particularly good language for parallel computing. You have to pay for commercial licenses, something like that. And then there's this migration of R to Python. And then if you look at the packages, Python like far behind in terms of scientific computing. It's more general computation. And then people start developing Python code, generalized Python packages to do this sort of work we do, right? And then unless Python is equipped with some kind of easy way into quantum computing, there has to be another language invented to basically pipeline everything into the quantum realm. So I think it's going to take some time.
Any other questions from the audience? Thanks. Oh, we should.
We're getting close on time and we have a small little transition with the rooms here. So
Okay,
let's
so
call it.
this is 3:15 is our.
Yes, 3:15 and then 3:30 will be the one.
Okay, any further question or last question? Sorry?
I'm gonna actually just say, if you want to ask any more questions, especially for the folks here, we have a lot of time to do some networking, especially after flash talks. Thanks again so much, panelists, and thank you, Jingqiu, for leading everybody. So we're gonna do a little 15-minute coffee break. We're gonna open up the rooms here and then flash talks at 3:30. Thank you so much.
Don't forget to see Alqamah flash talk.